In this unit, we're going to take a look at the normal distribution. We're going to look at the shape of the curve and then the empirical rule that deals with the area under the curve. Now, first up, the normal distribution is this bell-shaped curve here. You've probably seen it in many places. Now, take a look at this curve here. You can see it goes up and then it's symmetric. It goes down the same way. These tails of the curve, they keep going out to infinities, negative infinity. They approach the x-axis, but they never touch it. But the area under this curve, the area under that curve is equal to 1. Now, don't worry too much about how can it equal 1 when it keeps going out and out this way, out and out this way. This was a major problem in mathematics that was solved by Isaac Newton when he dealt with infinities and developed a calculus. But it is true that the area under this entire curve, even going out to infinity, is equal to 1. Now, there are two parameters that determine the shape and the location of the curve, mu and sigma. I'll draw two pictures. So first, we could have a curve that maybe is kind of flat like this. All right, now I'm going to draw this line here. All right, that's going to be p of x, and this is going to be x. This would be mu. So these curves are symmetric around the mean, mirror images of each other. Now I'm going to draw another curve. Starts a little lower, comes up higher, and I kind of missed it, but it looks like this. All right. Now, these have the same location, but they have different standard deviations. So I'm just going to make some numbers up here. This might be a standard deviation of 3. This wider curve here, that might have a standard deviation of, say, 5. All right, so remember, standard deviation measures the amount of spread. So this flatter curve has more spread around the mean, and this tighter curve up here, this would be, the data is compact more around the mean. That has a smaller standard deviation. Now another possibility is this. Let's draw our axes. Here's x and here's p of x. Okay, we could get, all right, I'm going to draw the same shapes here, if I can. All right, so this might have the mean here might be a 10, and it might have a standard deviation of, I'll put it on the other side. Maybe the standard deviation is 4. Okay, now I'm going to draw the same curve, same shape if I can, but I'm going to put it over here, and this mean might be at 18. Right, and that standard deviation still might be 4. All right, so if they have different means, the curve is just in different locations. So as the mean increases, the curve moves off to the right. Decreases, moves to the left. Higher standard deviations, the flatter the curve. Smaller standard deviation, the higher, more steep the curve. Let's take a look at some details of this curve. So our x-axis down here, this is our random variable, and it's continuous. Might be the time of something, and this is our probability axis is right here. That's p of x. All right, so you can see that the curve is symmetric, mirror image. That means 50% of the area is over here, below the mean, to the left. 50% is over here, to the right of the mean. Now, that means the probability of x, the probability that x is a value lower than the mean is 50%. The probability that x is a value higher than the mean is 50%. So like if this was the time to complete a task, maybe on the average it takes 20 minutes. So half the people would complete the task lower than 20 minutes, half the people would take more than 20 minutes to complete the task. Now if you come out to this curve, it's a little hard to see here, but maybe it's like right here and over here. This is called a point of inflection. Same thing over here. Now, that's where the curve goes from concave one way to concave another way. All right, so this is concave down, this is concave up. All right, that's called a point of inflection. And now once you have the point of inflection, then from the mean, I'm going to do this in this color, from the mean out to that point of inflection, this is one standard deviation. So from here to here, that's also one standard deviation. So for example, I'll draw a curve here as best I can. Now right there, why don't we put that mean to be, maybe that's 20 minutes. Now if I locate that point of inflection, maybe it's here. Do you think that looks good? You know, like it's kind of concave down here, concave up here. Okay, that would be one standard deviation. So now suppose we have this in our picture. The mean is 20, and maybe one standard deviation is, say, 7 units. Okay, the mean is 20 units, like 20 minutes. The standard deviation would be 7 units. All right, this would be one standard deviation, which is 7 minutes, say. Same thing on this side, over there. That would be 7 minutes. So one standard deviation out to that point of inflection. So from here down to here, this value to that value, that's all within one standard deviation of the mean. Now let me make another drawing here, and we'll say this. You draw this curve. Now you remember back in your algebra course, let me just draw one here. You remember doing things like this in algebra? If you graphed maybe, let's see, how about a simple one here? Let me get rid of those. How about we'll do a real simple one? Well, how about this one here? You remember that one? Terrible drawing. Y equals x squared. All right, so curves, some curves have different formulas for it. The normal curve has a formula also. Now, I want to find the area under this curve here. So if I do this, well, here's the formula for this curve, first of all. This will be f, and let's do p. All right, let's do p. Probability. All right, so this curve is, here's the function. P is equal to 1 over sigma times the square root of 2 pi times e to the negative, it's a fraction up here, x minus mu squared over 2 sigma squared. All right, that is the equation to this curve. That's the equation to this curve right here. Now, x squared is the equation to this one. This is, you can see, way more complicated. And then what I would have to do is, if I want to find the area under a particular part of the curve, like suppose I wanted to do this. You know what, let me get rid of this here. If I wanted to find this probability here, say I want to go from, say the mean here is 20, and I want to go from 22 out to 28. I want to find the probability that the random variable x lies in here. All right, what's the probability that, you know, on the average it takes 20 minutes to do something? What's the probability it takes a certain person between 22 and 28 minutes? Well, I would have to find this area right here. Now, how do I do that? I have to use calculus, all right? So use calculus to get this area. Well, I don't need to use calculus because somebody has done it all for us and put it in tables and built it into our calculator. But if I wanted to do that, here's what it would look like. The probability that, say, 22 less than or equal to x less than or equal to 28 would look like this. Right, here's the computation you would need. So just for fun, it is 1 over sigma square root of 2 pi, and this is called an integral sign. We're going to integrate from 22 to 28 e to the negative x minus mu squared over 2 sigma squared, and then I would write dx out here. Okay, I think this is hard to do. All right, this is a very hard thing to do. We're not supposed to say hard in math classes, but it is. It's a hard thing to do. But fortunately, it's all done in tables, and it's built into the calculator. right? So that stuff's already been done for us. We just have to get our calculator to do it. Now, we've used that formula to find some of these areas, and this is called the empirical rule. All right, so here's what it says. If you find the mean, right, so you find the mean. Now, if you go out one standard deviation to the left and one to the right, now you see that notation? All right, let's just talk about that. You start at the mean and you add one standard deviation. Or you find the mean and you subtract one standard deviation. Now, if you add one standard deviation, you're right here, right? There's the mean, and move over a standard deviation. Here's the mean, go to the left a standard deviation. So how much of the data is in here? All right, so within one standard deviation of the mean lies 68% of all the data. All right, so if you go one standard deviation from the mean, you've got 68% of all the data. What if it's two, all right, I'll say two standard deviations. How much have you got? All right, look at the picture now. Here's the mean. Go over two standard deviations. So you go two to the left, two to the right. You okay with the notation? Mu, the mean, minus two standard deviations. So the mean minus 1, 2. The mean plus 1, plus 2. So if you go over two standard deviations, all right, what do you get? You get 34 and 34 is 68, and this is 27. All right, so what have you got? You've got 95%. If you add those up, you get 95% of all data. All right, so all the data is, 95% of all the data is within two standard deviations. Now what if you go over three? All right, so you start at the mean, go 1, 2, 3 standard deviations to the left, right? The mean minus 3 standard deviations. And then the mean plus 1, 2, 3 standard deviations. So the mean plus 3, right? So now you're out here. What have you got? 99.7%. Right, so if you go 3 standard deviations, you're at 99.7% of all the data. All right, so if you're looking at a distribution and you go out within, if it's normal, you go out 3 standard deviations, you've got almost all of the data. Okay, I'm going to work through some exercises in the book. I think this is problem number 2 in the Braves and Braves 12th edition. Here's a normal curve. We want to find the mean plus 1 standard deviation and the standard deviation. Well, the mean, that's pretty simple to get, I think. I'm going to claim that the mean is here at 16. Now, what is mu plus sigma? Right, that's going to be the mean plus 1 standard deviation. Now, it looks like the way they've drawn it, that point of inflection is right here. You know, it's concave down, concave up. I think it's right there. So what would you say that distance is? Well, it's an 18, right? Mu plus sigma is 18, all right? So that's an 18. So mu plus sigma is 18. So what is sigma? Well, sigma is going to be the distance from here to here. So I think that's a 2. Here's another problem. I think this is problem number 6 in the textbook. So first up, how much area is to the right? Now, percentage of area, we're also talking probability. So how much area is to the right of the mean? Okay, now let's just draw a little picture here. Okay, if I draw a picture, maybe we can do it without, but let's just be sure. Right, here's the mean. How much area is to the right? Okay, so how much area is to the right here? Well, that is 50%. Okay, 50% of the area is to the right. Now, second part, how much area is between mu and negative 2 sigma, mu plus 2 sigma? All right, so if you go over 2 standard deviations, 1, 2, 1, 2. All right, so this one here is mu minus 2 sigma. This one here is mu plus 2 sigma. So how much of the area is, say, in here? How much of the area is between those? Okay? Now, empirical rule. Remember what it was? Empirical rule, it is 95%. All right, so 95% of all the data lies between those two values. And then the last one says, how much area is to the right of mu plus 3 sigma? Okay, now let's be careful. You know, I'm going to draw this again. That's a mess. All right, now there's the curve. Here's the mean. Go over 1, 2, 3 standard deviations. All right, so this is mu plus 3 sigma. Okay, we are asked how much area is out there. Oh, that blue doesn't really show up. How much area is out there? Well, we do know this. If you go between 3 standard deviations, right, between 3, oh, that's terrible. Okay, so between 3 standard deviations, what you get is 99.7%. Now, how much is left over, right? Because we want that 99.7, that's from here all the way here. That's all of this. How much is this? Well, how much is left over? Okay, that's going to be what? 0.03, and we want half of that, so divide it in half. So I'm thinking it's 0.015. All right, so I'm going to claim 0.015. This problem, I think, is number 10. So it says, vending machine automatically pours soft drinks into cups. The amount of soft drink to spin into a cup is normally distributed. All right, so here's what we've got. I'm going to draw a picture. I'll draw it up here. All right, so X is the amount, right, say this is the number of ounces. How about OZ? That's the number of ounces that go into a cup. Now, what do we know? We know that it's normally distributed, so I can draw that normal curve. And then it says this, with a mean of 7.6. So on the average, 7.6 ounces of soda goes into this cup. With a standard deviation, I better write this down. Mu is 7.6 with a standard deviation of 0.4 ounces. All right, so now we're supposed to answer the following questions. And it says, see that figure. All right, so let's look at that figure. Now, the figure was this one here. I'll put it up, but I'm going to try to draw it over here. All right, and I'll draw it bigger so I can actually write some stuff on it here. So the high point is 7.6. Now, one standard deviation is 0.4. So if I go over to one standard deviation, like that's where that point of inflection is, all right, so if I go over here, follow that down, and then I'll do it on this side too, this would be what? This is, remember what it is? It's mu plus 1 sigma, so it's 7.6 plus 0.4, that turns out to be 8. And if I do it down here, this is mu minus sigma, so it's 7.6 minus 0.4, so we get 7.2 ounces. Now that's one standard deviation. So what it's telling me right now is this. What percent of the cups will be filled with between 7.2 and 7.8 ounces? That's not a question here, but I can see it right away. Between 7.2 and between 7.2 and 8 ounces, we'll have what? 68% of all the cups in there. But now here's what we want to know. Estimate the probability it's going to overflow. Well, let's see. What have we got? Let's see. Oh, it's an 8-ounce cup. All right, well, here's an 8-ounce cup, right? So it's going to go to 8 ounces. So what's left over here? So the cup gets filled up to the brim right here, and then if it goes any more, it overflows. So we need to find this area. Find this area. Okay, well, what do we know? Right now, we are 68% of all the data is here. So how much is on the outside? Well, it's going to be 1 minus 0.68, which is 0.32. So 68% of the area is here. 32% is out here. And we want just the right half. So divide it in half. 0.16. All right, so part B says estimate the probability that the cup, oh, part A, we're doing part A. What's the probability that the cup will overflow? Well, that's going to be this. That's going to be this area out here. So the probability of overflow, this is the probability that x is greater than 8, and that turns out to be 0.16. All right, so it says 16% of all cups will overflow. That's how this machine is made up. 16% of all the cups are going to overflow. And then part B says, estimate the probability that the machine will not overflow. Well, if 16% overflow, all right, for part B, all right, I'll do part B way over here on the left. The probability of not overflowing, that's going to be 1 minus the probability that it does overflow. That's going to be 1 minus that 0.16. So what have we got? 0.84? All right. So, you know, if you got 16% over here, what's left over here? That's not overflow. All right. So this says that 84% of the cups will not overflow. All right. So we could actually say that 84% of all cups will not overflow. Now, part C. The machine has just been loaded with 850 cups. How many of these do you expect will overflow? Well, we know, right? 16% are going to overflow. So let's do that. Well, I can just do it right here. Okay, so what are we going to have? I'll do it right by the problem. 16% of 850 will overflow. So that's going to give us, what, 0.16 times 850. Now, I'll do that in my calculator. I didn't memorize that high in my multiplication tables. Times 850. I'm getting 136. Okay. So 136. So out of those 850 cups, we would expect 136 to overflow. All right, so that's a good start for the normal curve. Let's call it quits right here.